Okay, good morning, everyone. So today we'll start the second to the last module for the course, module 10. This will cover two independent topics. So for today, we'll try to discuss Romberg integration, which is an acceleration attempt for the uh, the trapezoidal rule. And then next meeting, we will be talking about anomalies in numerical integration. Kaya lang, I will be on leave on Friday, so I won't be able to meet you live, guys. So what I'll do is post the recording of the class that I will hold tomorrow for section V. So you can watch it, or you can also attend that class if you want to see it live. So it is 11:30 to 12:30 tomorrow. So that would be the second meeting for this week. Okay, so again, I won't be around on Friday kasi naka-leave ako on that time, right? Also on Wednesday next week, naka-leave uli ako. Sorry guys, but what I'll do on Wednesday is I'll give you a recording to watch, and that will be the start of module number 11, the last module for the class, which is about Monte Carlo simulation. All right. So that being said, it seems that the next time that we will see each other live would be on Friday next week. But the beauty of online learning, pwedeng ipapanood ko na lang sa inyo yung recording of the other class, or I will make an ad hoc recording of for Wednesday next week kasi naka-leave ako hanggang Tuesday next week. Or actually, naka-leave ako hanggang Wednesday. So, kaya may bagong recording akong gagawin for both sections for the first meeting next week. All right? And then next week, I'll also give the details for the final project. So I hope nagsimula na kayong mag-usap-usap kung sino yung mga kukunin yung ka-group. Hindi ko pa nga lang na-decide kung ilan per group. Have we decided ilan per group yung gagawin natin for the project? Hindi naman mandatory, so you can work on your own if you are more comfortable doing that. Pwedeng by pair, pero hindi ko pa na-decide ano yung maximum number. So probably it's either by pair or by at most 3 persons in a group. But if you have any suggestions, just let me know. Pero if finalize ko yung details next week. All right? So habang naka-leave ako, pag-isipan ko na yung guidelines nung problem set, nung final project, which will be due on the first week of January. Okay? So that being settled, so let's go to module 10. Okay. As I mentioned, may dalawang independent topics for this module. First, which is our agenda for today, Romberg integration. And then second is anomalies in numerical integration. Okay. So here are some readings. Of course, we have the work text here. I had to correct some typos in the work text last night. So may nakita akong typos pertaining to this module. So if you are using the work text, paki-download yung latest version na in-upload ko yesterday using the same link. So in-update ko lang naman yung file na nandun. The discussion on numerical integration anomalies can be found in Brady. So mas detalyadong discussion is on Brady. And then the derivation of the Romberg integration can be found in this lecture notes by Lambers. Hindi ko na kasi i-derive yung Romberg integration. We will be focusing on its application. Kaya medyo maiksi lang din naman yung lecture for today. Okay? So I put the links here so you can visit them. Okay, so far, what we have developed are two types of quadrature formulas, which allowed us to approximate the integral of any function, or actually not just any function, but a function that is not given explicitly to us, but rather given in terms of distinct data points. All right. So kung distinct data points yan, kaya pa rin natin kasi yung Newton-Cotes quadratures allowed us to just take the interpolating polynomial that will pass through all those data points and integrate that interpolating polynomial instead of integrating or actually instead of integrating the actual function na represented by those data points. And actually, kung masyadong komplikado yung integrand or walang closed form antiderivative yung integrand, Newton Cotes gave us the freedom to choose the exabytes nicely so that we will get an approximate to the integral by just using a linear combination of the function values, right? Tapos yung Gaussian integration formulas naman, they gave us a way on how to find the best abscisses and the best associate and the weights associated with them to get an interpolating polynomial that will give a quadrature formula that will give us exactly the integral of polynomials up to a certain degree, right? We learned that if we are using endpoints in the Gaussian quadrature rules, then we are sure that that the resulting integration formula can integrate polynomials up to degree 2 to the n minus 1 exactly. All right? Pero may ilang mga problemas pa rin kasi parang almost perfect na yung nagawa nating numerical integration theory. But again, there would be some problems with that. Parang hindi siya nawawala, no? Kaya parang ganun sa numerical analysis. Nagpo-propose tayo ng method. Then we will not just apply the method itself, pero titingnan natin ano yung pros and cons ng method. All right? So we're looking at the theoretical error, the error involved in the machine implementation of our method, then some other issues. And then we are also trying to improve our methods by addressing these concerns. Okay? So ano ba yung mga limitations ng mga quadrature formulas? For instance, kahit sinabi natin last time na yung accuracy ng composite rules ay theoretically independent of the step size, right? Pinakita ko to towards the end of I think module 8, I think. So, yung machine implementation yung machine implementation niya ay hindi necessary nagiging independent talaga of the number of subintervals used. Because the problem is the more subintervals we use, the more operations are involved. So mas maraming arithmetic or function evaluation tayong pinapagawa sa computer. And remember, computers are finite machines. So ibig sabihin, every after operation, meron siya mga decimal digits na tinatruncate na because it doesn't accept too long a decimal digit on its memory, right? Kasi halimbawa, yung Excel, designed lang siya for up to, say, 16 decimal digits by default. So when you multiply two numbers with 16 decimal places, all right, so makukuha mo ay um, another number of degree with at most a number of at most 32 decimal digits. Pero hindi siya kayang i-save or i-accommodate lahat ni Excel sa kanyang memory. So kukunin niya lang yung first 16 decimal digits. Tapos paulit-ulit siya. Kung marami tayong subintervals na ginagamit, mas marami tayong operations na ginagawa. So nagpapatong-patong yung truncation error na nangyayari. The more operations we perform, we are prone to losing many significant digits. So isa yung problema nung composite rules natin. And then also, yung paghanap ng optimal number of subintervals is much more cumbersome or much more tedious compared to the difference formulas. So if you remember sa numerical differentiation, we have one section that talk about looking at the optimal step size to get the perfect balance between the theoretical error and the machine implementation error, all right? Pero sa numerical integration, hindi siya ganon kadali. All right? So medyo mahirap mag-compute ng error bound for numerical integration formulas. That's why, if you remember, we didn't pay too much attention to it in the previous modules because medyo mas involved yung paghahanap ng optimal step size. All right? And also, actually, yung mga error bounds na nakukuha natin for numerical integrations are quite pessimistic. So, ibig sabihin, masyadong conservative o playing safe yung theoretical errors. So, what do I mean with that? Kasi di ba nakukuha natin madalas ay yung error or yung absolute value ng error ay less than or equal sa isang value. And this value, which we call the error bound, is the maximum possible error that we can find. Pero kung magbabasa kayo ng mga theoretical errors para sa numerical integration formulas, you will find that they are very conservative. Hindi sila tight. Meaning, kumbaga sasabihin niya, ito yung maximum error, pero posibleng yung error, andito lang naman. Kasi hindi natin makuha yung pinakamaliit o pinaka-tight na upper bound. So, kaya medyo negative o pessimistic yung error bounds na nakukuha natin. They could be much, much more larger than what the actual error is. Okay? So, ano yung implication niya? So, if you're looking for how many subintervals to use or how many iterations should we perform for this numerical method, we might end up doing so much work than what is required kasi nga pessimistic yung mga error bounds. So, halimbawa, sinabi ng error formula mo, okay, ganito yung maximum error. So, kukomputin mo, ano kaya yung number of subintervals that I will use? Halimbawa, compute mo ay 10 subintervals, okay? Para makuha mo yung or masigurado mo na na-satisfy mo yung error threshold. So pagka pinerform mo yung numerical integration using 10 subintervals, you might get much, much better result than what you needed. Kasi minsan nagtitipid tayo sa computing power. Or pagka, halimbawa, nag-simulate na kayo, nagre-research na kayo, some computations can take 10 hours, halimbawa, or even a day. Tapos deadline mo na bukas, hindi mo naman kailangan ng napakagandang approximation. Halimbawa, you're satisfied with the error of 1% lamang. So pag ginamit mo yung error bound, posible makompute mo kailangan ko ng 10 subintervals. Pero in reality, dahil pessimistic nga yung error bounds, mukhang ang kakailanganin mo lang pala ay 5 subintervals. So you did much work than what is required. May nasayang ka na na oras or computing resources. Okay? So these things are some limitations of the integration formulas that we have developed, which we would like to address by Romberg integration. Okay. So ano ba itong Romberg integration? Actually, Romberg integration is an application of Richardson extrapolation on the composite trapezoidal rule. So if you remember when we talk about numerical differentiation, we talk about Richardson extrapolation, which will use two approximates for the numerical derivative or for our approximate for the derivative to get a better approximation, right? Yung nakagawa tayo ng sequence na mas mabilis nagko-converge dun sa actual value. And as I noted there, yung Richardson extrapolation ay hindi limited sa numerical differentiation formulas. The one that we derived there is applicable to any other iterative formula of order of convergence 2. So kaya yung Richardson extrapolation, yung idea niya, pwede pa rin natin gamitin for for numerical integration. And when we apply it to the composite trapezoidal rule, what we will get yung Romberg integration formula. Okay? So since we have already seen how Richardson extrapolation was applied before, the derivation process for Romberg integration is very, very similar. Okay? So if you want to take a look at it, kasi hindi na natin siya mas bibigyang focus, you can find the derivation here in this lecture notes by Professor Lambers. So yeah, pwede niyo siyang sundan. Kaparehas na kaparehas siya, or actually yung process ay kaparehas na kaparehas nung ginawa natin sa numerical differentiation. Okay? And after that derivation, ito yung makukuha nating process. Okay? So let's first recall what the trapezoidal rule is. Okay? Actually, kailangan ko pala itong baguhin. You will apply the composite trapezoidal rule. Yeah, composite. Oops. Dapat ay composite trapezoidal rule ang gagamitin natin repetitively but using halved step sizes at every iteration. So para mangyayari ay start ka muna sa B minus A na step size. Alright? So B minus A na step size, perform yung trapezoidal rule, which is the simple trapezoidal rule. Tapos sa pangalawang iteration, hatiin mo yung previous step size. So kung ang step size mo kanina ay b minus a, ngayon ang gagawin mong step size is b minus a over 2. Perform the composite trapezoidal rule using that step size. Okay? Now, to keep track of everything that's happening, we will call the approximate using the trapezoidal rule with step size h by trap sub h. Okay? So, and then, yung Romberg integration, meron siyang dalawang indices. Okay? So, tawagin nating R sub kj, yung approximate sa Romberg integration on the kj iteration. Right? Ano yung tinatrack ni K at saka ni J? Si K, siya yung nagtatrack sa step size. Nakapang ilang step size na ba tayo? Tapos si J, ang tinatrack naman niya ay pang ilang level na ng extrapolation yung ginagawa natin. More on this later, pero dahil dalawa yung indices ng Romberg integration approximate, okay? So i-organize natin yung results into a tableau or into a table, okay? Na yung K number, that would be the row number that will tell us nakailang kalahati na tayo nung original step size. Okay? And then J will give us ilang extrapolation na yung ginawa natin or ilang beses na tayong gumamit ng previous approximations to get a new approximation. Okay? So let's see. All right. So that means yung R sub K1, right? So ibig sabihin, this would be step size K. Ang step size level niya ay K. Tapos yung 1 means isang beses pa lang tayo, or actually first level of extrapolation, which means nandun pa rin tayo sa actual trapezoidal rule. So in the tableau that we will develop, yung first column ay sila lang yung result using the composite trapezoidal rule. Tapos we will use an extrapolation formula kung paano mabubuo yung mga panibagong columns. Alright? So, ito yung pagbuo ng additional columns. So we will use 4 to the power j minus 1 times a previous approximate minus another previous approximate all over 4 to the j minus 1 minus 1. Okay. Ito pala yung binago ko sa handout last time. Ang step size ay b minus a over 2 to the power k minus 1. Okay, so exponent yung k minus 1. In the previous version, and I think in the work text, I wrote 2 to the power k, tapos naka-minus si 1 sa baba. Dapat 2 to the k minus 1 kasi yung Romberg integration nga, kinakalahati natin yung step size every time. So we will just be dividing b minus a by a power of 2. Okay? So it's just a bunch of formulas. Siguro it would be much easier if I will present this using a specific example. All right, paano siya binubuo. So before I shift to, I'll use Excel, but this might be more conveniently done using MATLAB kung magpo-for loop kayo kay MATLAB or Python. Pero para mas mapakita ko sa inyo yung nangyayari step by step, I will do it via Excel. All right? Pero again, it is more conveniently done using MATLAB or using Python. Gagawa kayo ng isang for loop para dun sa entire integration tableau. Actually, dalawang for loop pala. For loop inside a for loop kasi nga table yung itatry natin gawin. Okay? But before I shift to my spreadsheet, do you guys have any questions? Puro ano lang naman siya, puro formula so far, no? And for some, it's hard to appreciate the formula without deriving it and without seeing how it is performed, right? Pero sabi ko nga, yung derivation ay reading assignment na lang. Tapos, a bunch of formulas lang naman ito. So siguro, let's leave the process through at tingnan natin paano nga ba siya ginagawa. In your lab exer next week, kailangan nyo mag-perform ng Romberg integration. So let's do a practice So, kung walang questions, let's try to recreate the tableau in example 10.1. In this case, yung paborito natin so far na transcendental number ln2 ay approximate uli natin. But this time, we'll be using a 5-row Romberg integration tableau. Okay? So let me shift to my spreadsheet. Tapos try natin i-recreate yung table 10.1. Okay, so I hope you guys can see my spreadsheet at hopefully okay na yung size nung fonts. So just let me know if I need to increase the size here. Tapos kinopya ko na rin yung mga formulas dito sa right panel nung Excel kasi I'm really bad at memorizing things. So kaya kailangan kita ko yung formulas. This first formula over here, etong formula na to, etong ginagalaw ko, yan yung composite trapezoidal rule. Etong H, ayan yung formula dun sa Romberg integration. Remember, we are taking half of the original step size multiple times. And then here, ito yung extrapolation formula for RKJ. And we will see later ano naman tong formula na to, yung RNN minus Rn minus 1 n minus 1 all over 2 to the power n minus 1. Okay? So we are integrating so we are computing this. We want to integrate over the interval negative 1 to 2 yung function na 1 over x, right? Kasi ito yung magbibigay sa atin ng ln of x. Alright, so tingnan natin. Yung original step size, itong column A, lalagay ko lang yung original step size, column for H. So we'll start with B minus A. So that's gonna be 2 minus 1. And then we will repetitively get half of the step size. So kasi nga per row, remember RKJ, keep tracks of the step size, okay? So yung una, step size muna natin yung buong interval. So the step size will be B minus A all over 2. And then we'll take half of it for the next row. So i-divide ko lang siya by 2. Tapos ilang rows yung kailangan? 5 daw rows. So I will take half of it until I get 5 rows. So the next H should be 0.25, 0.125, and then 0.0625. So ito yung 5 rows ng Romberg integration tableau. Kulayan nga natin to. So ito yung okay. So yan naka-yellow, yan yung integration tableau, all right? So each row will correspond to different step sizes. Each column naman ay extrapolation yung iki-keep track niya, all right? So lagyan ko lang tong k equals 1, k equals 2, k equals 3, 4, and 5. Ito naman yung j equals 1, j equals 2, 3, 4, and 5. So yung first column, remember may note tayo na yung r sub k comma 1, or the first column in the tableau will be an application of the composite trapezoidal rule. Okay? So gawin natin siya. So, paano ko ba 'to gagawin ng mas maayos? Kaya sabi ko mas mas conveniently done sa MATLAB o kaya sa Python kasi nga sa bawat entry dun sa first column, lagi tayo nagko-composite trapezoidal rule. Okay? So sige, gawin ko siya primitively. So, gawin ko siyang, ito yung value ni H. Tapos, kailangan kong mula kay, maglagay ako dito ng, 0, 1, 2, 3, 4, 5. Tapos gawin ko tong 1 plus this guy times H. Okay. And then, eto. Alright. So, ibig sabihin ko, ang step size ko ay 1. Yung una kong abscissa na gagamitan ay x equals 1 at saka x equals 2. So, ito yung dalawang abscissas na gagamitin ko dun sa trapezoidal rule. Tapos, kukunin ko yung function values nila. So, f of 1 is 1 over 1. F of 2 is 1 over that guy, all right? 1 over the abscissa. So ito yung dalawang function values na gagamitin ko, all right? And then following the trapezoidal rule, ang value lang nito ay trapezoidal rule, no? So this will just be b minus a. So that's going to be 0.5 times the step size times the sum of f of a and f of b. So times sum, itong dalawa. Okay, so here we go. So ito yung approximate using the basic trapezoidal rule. Okay, 0.75. Okay, and that would be the first row, the entry on the first row and first column. First row kasi original step size, first column trapezoidal rule, plain and simple. Okay, and that's the only entry for the first row. Dun sa pangalawang row naman, okay, remember yung pangalawang row ay kalahati yung step size ng previous value. So kung kalahati siya ng previous value, okay, ang step size niya na ay magiging 0.5. Hide ko na itong ginamit ko para sa step size na to. So dito naman, magpa-perform ako ng composite trapezoidal rule na ang step size ko ay 0.5. Okay, so ibig sabihin ito, hold on, bakit hindi siya gumalaw? 1 plus B15 times A16. Okay. Right. So, ito dapat ay, hold on. Dapat ito ay hinold ko yung column number. There we go. So, the 0.5, kailangan ko naman ng tatlong points. All right. So, I'll start with x equals 1, then x equals 1.5, and then x equals 2. Ito naman yung mga x's na gagamitin ko para dun sa composite trapezoidal rule with step size 1.5. Tapos, computing ko yung function values. Ito yung mga function values na kailangan kong gamitin. And then we will refer to the formula for the composite trapezoidal rule. Ito siya. Siguro lagyan natin to na okay, ganyan muna natin siya. So ito yung formula ng trapezoidal rule, ng composite trapezoidal rule. Gamitin ko siya with step size 0.5. And that will give me the second row, first column entry in our tableau. So this will just be step size, which is 0.5, divided by 2 times, okay, function value at the first endpoint plus twice lahat ng intermediate points plus the function value at the last point. Okay, there we go. So ito naman yung approximate to ln2 using the composite trapezoidal rule with step size 0.5. So, dahil ngayon, meron na tayong dalawang estimate using the composite trapezoidal rule. Actually, yung una pala, using the basic trapezoidal rule kasi 2 points lang yung ginamit. Yung pangalawa ay using 3 points. We can use the acceleration formula, yung formula para kay RKJ to get a better estimate. Okay? So, ano yung formula? So, implement natin siya dito. This would be equal to 4 to the power j minus 1, so si j ay ito, minus 1, times rk, comma j minus 1. So ibig sabihin, ang k natin dito ay 2. Tapos, yung previous column. So that would be r sub 2, comma 1. So ito yon 2, comma 1. Second row, first column. Minus yung nasa previous diagonal, r sub k minus 1, j minus 1. So, ma-minus ko to. Kasi ang k ay 2 natin, ang j ay 2 ngayon. So, k minus 1 and j minus 1 are both 1. So, ang subtrahend natin dito ay yung nasa 1, 1 entry dun sa tableau. Divided by 4 to the power j minus 1. Okay, j minus 1. Tapos may minus 1 sa labas. So this guy would be our best approximation so far, 0.69444. Okay. So nakita nyo, ano lang talaga siya, basic application ng mga formulas na nandun sa module. So wait lang guys. So try ko tong gawing mas Tinatry ko siyang i-generalize para mamaya hihigitin ko na lang siya. Kaya lang, tingnan ko kung may mga magmo-move. Let's see. Okay, fix dapat yung D. Fix dapat yung D. Alright, so if you are familiar with Excel, you know what the dollar signs in the formula does. So ang ginagawa niya ay pag hinigit mo siya, hindi magmo-move yung row or yung column number. Actually, gusto ko palang gumalaw yung column number. Ayokong gumalaw yung row number. So, lagay ko siya sa unahan. I think this should work. Okay. Now, to get the third row in our table, we'll perform composite trapezoidal rule ulit, pero yung step size natin ay 0.25. So, I'll hide this guy. Makita nyo, mas efficient nga siyang gawin, di ba, kung nasa loob kayo ng MATLAB o Python na yung mga for loop para dun sa composite trapezoidal rule ay hindi na natin ginagawa manually. Pero gusto ko siyang gawin sa Excel para ipakita sa inyo kung ano yung nangyayaring process. Okay? So, sa susunod na row, itong i-fill up natin, row number 3, okay, yung first column niya will require us to apply the composite trapezoidal rule, but this time 0.25 na yung step size. Okay? So, 0.25 yung step size. So, gagamitin ko si 1, si 125, si 15, hanggang kay 2. Ito yung mga x's na gagamitin natin. Kasi ito yung mga function values na paglalaruan natin. Alright? And then if I apply the trapezoidal rule, this will be half the current step size times the summation of function values. So kunin mo yung function values sa lower limit plus twice ng sum ng mga function values sa gitna plus function values sa dulo. That will give us the approximate 0.69702. Tapos again, para makuha yung second column, kailangan nating i-apply yung Romberg integration formula. Dahil ginawa ko na siya sa 2,2 kanina, para kay 3,2, try ko ang higitin. Sana walang, nagka-problema ako sa paghigit dito. Ano yung nag-move na ayoko? Okay. So, nag-move pa rin yung, okay. Baligtad nga yung ginawa ko. Tama na pala yung kanina, no? Dapat itong dollar sign ay nandun pala after nung o before yung row number. Kasi yung row nga pala yung ayaw ko mag-move. So, gawin ko yan. Okay, yeah, there we go. I think that's better. Double check ko lang kung ito yung value dun sa table 10.1. Yes, I think that's it. All right. So, ito na yung best approximate natin. Yung nasa 3, 2. Tapos, para makuha yung third column, mag-extrapolation uli ako, pero the extrapolation will be done on entries on the second column of the tableau. Alright? So, dito naman sa dalawang values na to, sa 0.693, dito, at saka dito sa 0.6944 ko i-apply itong Romberg formula na ito. So, ito naman yung focus natin ngayon. Okay? So, ito naman yung formula na gagamitin natin. Pero ngayon, ang J na natin ay 3. Ang K na natin ay 3 kasi nasa third row na tayo. Tapos, yung J natin ay 3 kasi ang ginagawa na natin ay nasa third column. Alright? Tingnan ko ako mag-work pag hinigit ko na lang ito. Pag hinigit ko to, 69317. Yeah, and I think that's it. The double check natin, okay, ginamit ko yung dalawang previous approximates from the previous column and ginamit ko itong nasa taas. And there we go. Okay? And then gagawin niyo lang to paulit-ulit hanggang mabuo yung number 4. dito ka magsisimula. Gagamitin mo yung composite trapezoidal rule dito. Okay? With step size 0.125, makukuha mo tong entry rito. Tapos para makuha yung entry dito, gagamitin nyo yung Romberg formula, the extrapolation formula for Romberg using these two guys. Okay. Ito namang dalawang values yung gagamitin natin, itong mga naka-highlight na green, para makuha itong entry na to ng Romberg. Okay? So makukuha mo tong number na to, itong may nakasulat na Romberg. So makukuha mo yung value niyan. And then to get this entry, the entry on the fourth row, third column, ang gagamitin naman natin ay etong dalawa. Itong dalawang previous values na to ang magbibigay sa atin ng entry para sa 4, 3. Tapos para makuha yung 4, 4, gagamitin naman natin etong dalawang previous values na to para mapunan ito. Okay? At madali lang naman siya kasi gagamitin niyo yung Romberg integration formula, yung Romberg extrapolation formula na ito. Okay? So, yun. Medyo matrabaho kung i-complete ko pa kasi kailangan ko yung trapezoidal rule. Pero after kong ma-perform yung trapezoidal rule, higitin ko lang naman yung formula kasi simple yung Romberg extrapolation technique. Okay? So, is that okay? Or do you think I'll need to perform the trapezoidal rule pa for row 4 and 5? I hope you can recreate a table on your own. Okay? What do you think, guys? Okay na ba yon? Pero sige na nga, hindi naman siya ganun kahirap. Tuloy natin, sige. Okay. Practice makes perfect, perfect din naman. So, hide ko lang to para mawala sila. Okay. Ngayon, ang step size na natin ay 0.125. Okay. Nawala yung formula ko. So, this would be 1 plus this guy times the step size. So, as always, mag-start tayo sa x equals 1. Tapos, magpapatuloy tayo hanggang, anyari? Okay. Dapat yung step size ay hindi nag-move. So, dapat ito ay, okay, meron to dapat dito. Baligtad ba na, okay. Baligtad yung nagagawa ko. So, 1. P24. Ano yung ayoko mag-move? Ayoko mag-move yung column number. Baligtad ang nilalagyan ko sa Excel. Okay. So, kailangan ko pala ng 6 na points. Actually, 8 points na para dun sa susunod na step size. Let's see. 1, 1, 2, 5. Kulang pa rin ako. Okay, there we go. Tapos kukomputin ko yung mga function values. Okay. Pinakamatrabaho dito yung paggawa ng trapezoidal rule. So ito yung mga function values. So dun sa first column ng fourth row, magta-trapezoidal rule lang ako. Kalahati nung step size times sum ng mga function values, yung nandun sa upper and lower limit ng integral, sila lang yung idadagdag ko, plus 2 times the sum of the intermediate values. So twice the sum ng mga nasa gitna. Okay. And that will give us that approximate. For 1. Okay, I think that's fine. Tapos mag-Romberg integration ako. So ikitin ko to. And it will use those previous guys, the previous approximates. Tapos gagamitin ko yung J column. Tapos higitin ko lang naman siya hanggang 4, 4 para makuha yung 0.69315. Actually, if we increase the decimal digits here, yeah, you'll see what was in the table. Okay. So ano nangyayari dito? The best approximates are always on the diagonals. Okay. So ibig sabihin, ito yung best approximate using one round of Romberg integration, or actually using zero Romberg integration. After the first Romberg extrapolation, ito na yung best, yung nasa 2, 2. Tapos susunod yung nasa 3, 3, tapos susunod yung 4, 4. Yan yung mga best approximates natin per row. Okay? So ang kagandahan sa Romberg integration, sabi natin pessimistic yung error bounds para sa numerical integration formulas. So Romberg integration allows us to perform repetitive approximations, tapos pwede natin itong i-fill up row by row. Kasi kung sa, halimbawa, kung sa composite trapezoidal, yun lang yung gagamitin mo. Tapos sabi ng formula, nagbabaka sakali ka na yung 5 iterations might give, or 5 subintervals might give us good approximate. Okay? So pinerform mo yung trapezoidal rule using 5 subintervals. Pero nung nakuha mo yung approximate, hindi ka pa ganon ka kumbinsido. So, dadagdagan mo ngayon yung subintervals. Gagawin mo say 6 na subintervals. But that will require you to start from scratch. Kasi iba na yung mga function values mo na gagamitin. Alright? Kasi uniform step size kasi yung trapezoidal rule. So, pagka gusto mong magdagdag ng subintervals, you have to redo all the calculations from scratch. Pero sa Romberg integration, pwede mong kompletuhin yung table one row at a time. Okay? So halimbawa, gawin mo lang yung first row. So ang approximate mo ay 0.75. If you're happy with that, then good. Kung hindi ka pa masaya dun sa approximate na 0.75, pwede mo siyang improve by adding one row in the Romberg integration tableau. So after you have constructed the second row, your best estimate would be on the second row, second column, yung 0.69444. Kung masaya ka na dyan, edi good. Pero kung hindi ka pa dyan masaya, pwede ka pa magdagdag ng isa pang row. Pero yung pagdadagdag natin ng row did not require us to recompute everything again from the scratch, because we'll just need to perform another instance ng composite trapezoidal rule, tapos puro extrapolation formulas na lang yung ginagamit natin. So basically, we can do this process, and after the addition of each row, we can decide, are we good or satisfied with the current best approximate so far? So pwede mo itong gawin without knowing what's the theoretical error bound. So parang every after iteration, pwede kang magtanong, na-satisfy na ba yung error threshold ko? So hindi natin kailangan mag-rely dun sa mga napaka-pessimistic na error bounds. Okay. So if madali lang i-determine kung kailan ka titigil kung alam mo yung actual value ng integral. Okay? So pwede kong gawin ito, 0.75 minus ln2 divided by ln2, that will give me the relative error. Kung satisfied na ako dun sa relative error na yon, then I will stop, right? Same thing goes for 0.69444 and so on. Kunin ko yung relative error niya sa ln2. If I'm good with that, then titigil na ako, right? Pero most of the times, hindi natin alam yung eksaktong value. Nagkataon dito sa simple example natin, alam natin yung actual value na gusto nating approximate. So kaya nating ma-compute yung relative error. Pero paano natin malalaman kung titigil na tayo? What would be our measure of error? Ang measure of error natin dito ay yung tinatawag na relative computable error estimate. Okay. So ito yung titingnan natin, yung relative computable error estimate, or RCEE. So yan yung itatry kong i-compute dito. Ang formula para sa RCEE ay ito. Okay. Tago na natin yung mga formulas na hindi na natin ginagamit. Ito. Alright? So, kukunin natin yung difference between the two best approximates per row. So, yung mga nandun sa diagonal, divided by 2 to the power n minus 1. Or actually, pwede natin itong tingnan as k minus 1. Para makuha ko yung gaano nagbago yung dalawang best approximates with respect to the number of halving of the step size. So yung RNN minus RN minus 1, N minus 1, siya yung nagsasabi gaano kalayo yung dalawang best approximates natin coming from the previous rows. Pero gusto kong tingnan yung relation niya to the number of times we took half of the step size. Kasi titingnan natin dito, may significant effect pa ba yung pagpapaliit ng step size doon sa best approximates na nakukuha natin? Baka naman hindi na ganun kalaki yung pagbabago dun sa mga values na nakukuha natin after taking half of the step size. Kung hindi na ganun kalaki yung pagbabago, then there's no point to adding several more rows. Okay? So I did this computation for the second row. Okay? So, kukunin ko dito yung relative computable error estimate. So, kinuha ko lang yung difference between D6 and D5. So, ito yung dalawang diagonal, yung blue at saka yung red. Divided by 2 to the power column number minus 1. So, nasa second column tayo. All right? So, that would be 2 to the power 2 minus 1. So, purple minus 1. So, ibig sabihin, meron akong 2% or 2.7% difference between the two best approximates we get so far with respect to the number of times I took half of the original interval. Dahil, so dito ang n natin ay 1, so divided by 2, so ibig sabihin, 1 time pa lang tayo naghati ng interval. Okay? Tapos titingnan natin ano yung mangyari sa susunod. So I'll just drag, madadrag ko ba to? Parang hindi ko siya madadrag, pero kunin ko to, yung RCEE para sa third row, would be yung entry sa 3, 3 minus yung entry sa 2, 2 divided by 2 to the power 3 minus 1, right? So, ibig sabihin, ito na lang yung pagbabago. Meron na lang akong 0.032% difference. So, you can decide, is that 0.32% difference significant enough for me? If it is, then tigil ka na. Ito na yung approximate mo. Pero kung hindi ka pa satisfied dyan, alright, pwede mo pang ituloy. Magdagdag ka pa ng isang row number. Okay? Dagdag mo tong fourth row. Tapos, para malaman, titigil na ba ako, kunin mo ulit yung RCEE. So, ikaw yung magbibigay ng threshold para dun sa RCEE. So, if you want, mali na pala to. You can set what would be your tolerance for the RCEE. Usually it's 10 to the, let's see. Usually it's 10 to the minus 8, but that is actually just an ad hoc estimate. So you can set it up, or kung merong ipapasolve sa inyo, sasabihin kung ano yung threshold para sa RCEE. So ito, maliit na, 10 to the minus 6 na yung RCEE. Okay? So say, kung ang RCEE threshold ko ay 10 to the minus 8, so ibig sabihin kailangan ko pang magdagdag ng isang row. And I think there, yes, 1.8, let's see, ilan na yung makukuha dito? Yeah, this one will give me, I think something that is less than 10 to the minus 8. So you can now stop, all right? So yun, I think that's it for the Romberg integration. Mas ano siya, mas computational compared to our previous discussions last time, wherein masyadong theoretical naman yung ginawa natin. Okay? So I think that's it for now. Do you guys have some questions? Balik ako sa meeting. Right? Ito yung mga klase ng discussion na pinaka-ayokong gawin. Yung masyadong mechanical. Kasi feeling ko hindi ko siya na-discuss ng maayos. Pero if I didn't do it satisfactorily, so you can just take a look at the formulas on the module and try to do it on your own, right? So one thing that you can take advantage of is kung natago nyo pa yung code nyo para sa composite trapezoidal rule. So pwede nyo siyang gamitin tapos dagdagan na lang ng Romberg integration formula. So kung mapapansin nyo dito sa 174, ginagamit pa rin natin yung mga previous codes na ginawa nyo. So it's a nice practice kung tinatago nyo siya kasi yung lines of code na ginawa nyo dati, pwede nyo siyang i-upgrade, parang i-update into a version 2.0 or 3.0, which will include some more features, right? Nadadagdagan siya ng improvements. Kasi ganun naman sa numerical analysis. Magde-design ka ng algorithm para ma-approximate ang isang bagay, tapos may makikita kang pros and cons, tapos itatry mong i-address yung mga cons. Usually, may dadagdag kang iba't ibang layers dun sa program hanggang makuha mo yung best possible program or method para sa yung specific application. Okay? So I think we can stop here. And yeah, it's just 2 minutes over time. But do you guys have any questions before we call it a day? Okay, so yes, Lyra, may gusto kang tanong? Nakita ko nag-unmute ka bigla. Okay.
Wala po, sir.
All
Thank you po.
right. Wala rin daw si Michelangelo. All right, so I think that's it. So again, guys, naka-leave ako hanggang Wednesday next week. Mag-RNR ako ng konti. So magbabakasyon lang ako ng konti before going back next week. So we'll see each other live na uli on Friday next week. But for Friday's class, papanoorin nyo yung recording ng klase ko bukas dun sa kabilang section. But if you're free and you want to join live, you can join us at 11:30 to 12:30. Nakalagay sa Canvas kung ano yung link. Hanapin yung link para sa klase bukas. Or pwede nyo na lang namang antayin yung recording. It would be live sa MS Teams kung member kayo ng group. A couple of minutes after we hang up the call, makikita nyo na yung recording. If kung wala kayo sa Teams, i-upload ko naman siya sa Canvas yung link. Siguro mga at most an hour after the class. Baka mag-lunch muna ako after ng class ko bukas. Tapos saka ko i-upload sa YouTube yung recording. Tapos sa Wednesday, dahil hindi rin ako makakapagklase ng Tuesday dun sa kabilang section, so kailangan ko mag-record ad hoc. So walang makakapanood sa akin ng live for the first meeting next time or next week. So ipe-premiere ko na lang yung video probably 11:30 to 12:30 on Tuesday para dun sa first section. Join the live kasi nasan ba ako nun? Nasa biyahe na siguro ako pauwi nun. So pwede ako mag-comment dun sa premiere. So kung may mga tanong kayo, pwede kayong magtanong dun sa YouTube video. Okay, I'll try to join you live. And then, or if not, just watch the recording on Wednesday morning para in time for discussion Friday next week. Kasi medyo connected yung discussions natin next week. Hindi katulad ngayon na ibang topic na yung i-discuss natin sa Friday o yung papanoorin nyo sa Friday. Next week, medyo connected yung lecture 1 at saka lecture 2. So I would appreciate, or it would be best if you can watch the recording on Wednesday before going to the class on Friday next week. Kasi nga part 1 at part 2 yon. So, okay. So I think that's it. So thank you guys for joining me today. And I will wish you na a good weekend kasi we'll meet na next Friday. Okay. Bye guys.
Thank you, sir.
Thank you po, sir.
Salamat po,
All
sir.
right.